I'm Dr. Maya Dunne. I'm trying to explain you the chapter 15 chemical equilibrium that we have to do in this week. So if you look at the this chapter, go up, okay. So it is we talk about chemical equilibrium. So a chemical equilibrium, it's because we said how the reaction, when the reaction start, the products forming, reaction consume, and how these processes are happening. So some reactions, okay, the reactant products, and sometimes the products also going towards the reactant. So if you see, if you showing these double arrows, that means reaction is in the equilibrium. Forward reaction and the reverse reaction happen in the rate. So this single arrow means it's only at one end. Reaction goes to product, stop. But then the double arrow indicate reaction is at the equilibrium. That means forward reaction happening, reverse reaction also happening. So we call when there's a no change of the forming of products and reactants using, we call the reaction is in the dynamic equilibrium. That means forward reaction and the reverse reaction happens at the same rate. So the rate of forward will equal to the rate of reverse reaction. That time we call it a dynamic equilibrium. Always, so how do you, so this, let's take this reaction. Always products divide by the reactants. We call K as a rate constant, sorry, equilibrium constant, and this is a C brackets we call concentration of products, concentration of reactants. K is equilibrium constant. So if you take this particular equation, these are the products. In NO2, 4 times the coefficient, O2, 1, and N2O5, 2 times. And this is how you find the equilibrium constant for this reaction. So if I ask you how to write the equilibrium constant for this one, how do you write it? K equals, let's see, let's make it a pen, okay. Yeah, that's good. So K, oh, that's good, equal H2 concentration, right, square Y, because this coefficient comes up, plus then multiply by CO, nothing, because it's just 1, and then you divide by CH3OH concentration. Oh, okay, that's it. I have the answer. Let me show you. So here, it's like that. Okay. So by looking at the K value, so K is higher K, that means more towards the products, right? K is less, that means more towards the reactants. In this particular case, you see K is very large number, above 1, that means you have more HBr forming in the reaction. So K is smaller than 1. When the reactant reaches equilibrium, there will be many more reactant. Okay, so this is how you write it. This is the K for the forward reaction. This is K, same reaction. If I ask you to write the equilibrium constant for the forward, these will be the products, right? These are the reactants. But if I ask you to write the K for the reverse reaction, these are the product. K reverse would be what? These will be the products, right? That's what I should write it here. Always K forward equal 1 over K reverse. It's opposite. This reaction, this is showing you when the reaction happens in several steps. A plus B gives you C. So see it like that. And then so 2A squared like that. So this is what I was talking, the multiple steps, A, B and B, C. So B over A, and then this one C over B. So total reaction is K equal K1 into K2. So the B's cancel out. Finally you get the final reaction, C divided by A, like that. So K3 is the total equilibrium constant. K1 is for this particular reaction. K2 is for this particular reaction. So the total K So this is how you write K1 into K2. So if I ask you, consider the chemical equation and equilibrium constant for the synthesis of ammonia, it's given K, but I'm asking the equilibrium constant for this particular one. It is not just inverse, right? You have to divide by 2 as well, because there's a, this gives you for the 2 ammonias, but I'm not asking for 2 ammonias, I'm asking for 1. So let's say so 2 ammonia, so 2 NH3, K reverse by half. So this would be the answer. So that's what you do. So it's K is reverse is this one, but we're not talking 2. We have we have only 1. So then K equals K half. So K half, and then 1 over divide and multiply by the half. So that's what you do. Same way, you can write the equilibrium constant. So far we wrote in the concentration, we can write it in the in terms of pressure as well. This is how I write in the pressure. Why? Because you know PV equals, wait a minute. Okay, so similarly we can write the equilibrium constant in the terms of pressure, because you know PV equals nRT. Let me show that down. Show a little bit. What is number of moles? Number of moles equals so concentration equals N divided by V. You take N, you divide V both sides. So N divided by V is concentration, P divided by RT equal concentration. So then that's what you can write, Kp equals Kc over RTN. So this shows you the, you can express the equilibrium constant in terms of pressure or in terms of concentration. So this one express nitrogen monoxide, a pollutant in automobile exhaust, is oxidized to nitrogen dioxide in the atmosphere according to the equation Kc. So Kp, so you use this equation, which is Kp equals Kc RT, so see delta N only for these two. So you write, okay, delta N is so you can plug these numbers. So -1 is RT, because delta N is this side you have 2 number of moles, this side 3, 2 subtract 3, -1, that negative delta N is -1. So you apply this one and then get the answer. Please practice this, applying these numbers with the calculator. And then heterogeneous equilibria, only we get the concentration only if it is a aqueous form. So you can write the equilibrium constant in the gaseous form, H plus, carbonate ion, carbon dioxide gas, not for the water, it's a liquid, so we don't have to get the concentration, same as for the solids. So if you have this one, it's we don't take this one into the equilibrium formula, because this is a heterogeneous. Solids does not include in the equilibrium constant equation. See, it's only we write carbon dioxide gas, not this one, because it's both are solids. So how, I have a question. So far we learned these things. My question is, consider the following reaction: carbon monoxide combining with hydrogen form CH3OH, which is methanol. A reaction mixture at 780 degrees initially contained carbon monoxide 5 molar and hydrogen 1 molar. At equilibrium, the carbon monoxide concentration is 0.15. What is the value of equilibrium constant? We know equilibrium constant K equals equilibrium concentrations of products, which is CH3OH, divide carbon dioxide, hydrogens twice. So we need equilibrium constant. So we don't know. We know equilibrium constant at equilibrium, carbon monoxide is 0.15. That's what we know. So how do we do that? In order to do this kind of a calculation in equilibrium, main type of calculations are the ice format. So we have, I'll show you how the ice format work. So this is ice. This is ice format. So it's initial concentration, change, equilibrium. You know, initially, at the beginning of the reaction, you have carbon monoxide, right? 0.5, hydrogen 1. Equilibrium, carbon monoxide concentration we know, which is 0.15. What is the change? Change is 0.35, right? 5 because at the equilibrium you have 0.15 remaining from the 5, so 0.35 react. So you know this reaction is 1 to 2. So then what about this one? If 1 react, 0.35, 0.7, right? So negative 0.35, 0.35 into 2, 0.35 form, because this reaction, we look at the stoichiometric ratio, 1 to 2 to 1. So, and then we subtract, okay, it's 0.3 and plus 3.5. Then we have all these numbers, and then we plug into the now calculator. 0.35 divide carbon monoxide 0.3. That's how you do it. This is we call the ice format. Very easy to do the equilibrium constant calculation. Let's do another one. Reaction quotient. Reaction quotient. So far we talk about reaction at the equilibrium. What if reaction is not at the equilibrium? Reaction is not at the equilibrium. It's the same thing. Instead of we call it the equilibrium constant, we call it as a reaction quotient, Q. Same way you calculate it. You can calculate reaction quotient in concentration or in terms of pressure. Depending on the Q, you can say which direction it goes. Q is greater than K. That means products will decrease, because as K great means you have more products. Q is greater, K is small. At that time, we say product will decrease and the reaction will increase. Q is small, products will increase, reactant will decrease. Q equal K, it's an equilibrium. So if a reaction mixture contains just the reactant, that means Q equal 0, because it hasn't started. Just the products, it means it's just one direction, it's infinity. So this is the reaction. So A and B are the so A form B. At the beginning you have only A. Slowly it goes down 0.75, like that it decreases, but at the same time products increase. So that's shows the relationship. Here this is K. K is same for the whole thing. Slowly A decrease, right? But here Q smaller. That means you have Q small means you have more. So the reaction runs to the right, right? Reaction run to the right, but Q equal K, it's in equilibrium. This one reaction runs to the, so it's the same thing here. Q smaller than K, reaction proceed faster. In the reverse reaction, less products, right? Wait a minute. Q smaller than, the products will decrease. Yeah, here reaction proceed to the reverse reaction. Yes, this is a reverse. Yes, okay. So consider the reaction and its equilibrium constant. So here you find the reaction quotient, and then we know Kp is 81.9, Q is 10. That means Q is smaller than P. That means the so Q smaller than P means reaction will proceed to the right. More products will form. Okay. So finding equilibrium constant, how we do it, first you have to find which direction it will proceed, Q to K, and then you make the ice format, and then you can solve X. So initial change equilibrium, always like A to B, initial is A form B, at the beginning you have 1, negative X, 2 twice, because it's like that. So it's the easiest way to think of the ice format. At the beginning you have only reactants, no products, negative X react, this is twice because it's 2B, and then 1 minus X, 2X. So let's look at this reaction. Finding the equilibrium concentration from initial. So this is a reaction, N2O4 to NO2, case is given, a reaction mixture 100 Celsius, initially contain NO2, find the equilibrium and concentration of NO2. Okay, so now you write, okay, initially 1 of NO2, and then change is so here is a reaction. At the beginning you don't have any reactant, you have only products, and then Kc is given, this initial amount, no product. So at that time you can say, okay, 2x plus x, and then so here you see what you do. You can't just use these numbers because the that's not the way. So you do write that way, and you find the Kc. Okay, so here you have to go like 2x and the quadratic equation. I want to tell you, I'm not going to go into the quadratic equation when I give you a question. So you can assume in this kind of a situation, 0.1 minus 2x, there's an assumption. The assumption is x is extremely small. So what happened when you subtract extremely small number from 0.1? It's same 0.1, right? So you can easily mark it off and then go with 0.1 divided by x. So then it's not that complicated. So in that way you can find that thing. So if you see x, like that, I'll ask the question, and then there is another question you can look at. It's in terms of pressure, same ice format, always use the ice format. And this is first I want to show you this one. Initial pressure, Q, and predict, use the so K is, we know K is 81.9, Q, it's the given time, and this particular time Q is 1. So that means K is higher. K is higher means reaction will proceed to the right side, right? I mean more products. So yeah, always I use the approximation that 1 minus x equal to 1. So this shows here, you see, show here, x minus ax is extremely small, so it's basically x initial. So this kind of a question I did using the approximation, you can see, using the ice format. See, it's 0.25 negative 2x. I assume it's 0.25. So you see that in the calculation, I assume this x is very small. And then I don't have to worry about it. I don't have to go to the quadratic equation. In the exam also, I'll stay away from the quadratic. So that's about in this chapter. And look at the Le Chatelet principle. The gas phase. Like that. So I practice all this calculation, and I hope this help you to understand the chapter. Thank you.